All right, so we just had an introduction about Rolle's theorem. We will revisit Rolle's theorem in the mean value theorem video as well if you need a refresher on that. But today in our list of topics for Unit 3, we're going to be applying Rolle's theorem analytically is going to be our focus. Hopefully my pen keeps up here. So let's jump right into it. Our first example, 1 of 3, says verify Rolle's theorem. Well, remember, to verify Rolle's theorem, there's 3 conditions that need to be met. First of all, f of x, which for us is cosine of x, f of x needs to be continuous on the closed interval that's provided. Because f of x is continuous everywhere, our f of x will definitely be continuous on the interval from pi to 5 pi. F of x needs to be differentiable. Well, how do you check if something is differentiable? It means you are able to take the derivative. So, to be able to take the derivative on the interval from pi to 5 pi, we have to consider what is f prime of x. Well, f prime of x is going to be negative sine of x. Is this derivative continuous on pi to 5 pi? Yes, which means that f of x is differentiable. We are able to take the derivative because the derivative is continuous on the open interval from pi to 5 pi. And our last condition that we need to check is f of pi equal to f of 5 pi. This will be the last one that we need to check. Well, let's find f of pi. The cosine of pi is going to be negative 1. And f of 5 pi, if we think about the unit circle, 0, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi is coterminal with pi. So we also get a negative 1 value for cosine. Because this is true, Rolle's theorem will apply. So because of these 3 things, f of x is continuous, f of x is differentiable, and f of pi equals 5 pi, by Rolle's theorem, there exists C on the interval from pi to 5 pi such that f prime of C is equal to 0. And again, the reason why this works, okay, we're thinking about those extreme value theorems. Let's think about cosine on pi to 5 pi. So we'll count by pi. Pi, 2 pi, 3 pi, 4 pi, 5 pi. If I were to start drawing a cosine graph starting at pi, then at 2 pi, we're up at 1. 3 pi, we're back at negative 1. 4 pi, we're up at 1. 5 pi, we're down here. So because the secant line slope is equal to 0, there will be at least one tangent slope that's equal to 0, which in this case would end up happening at 2 pi, 3 pi, and 4 pi if we needed to actually find the C value. Here it said just verify. Okay, but this one says to verify and find the values of C. So the first thing is we need to figure out what does this graph look like. Okay, so is f of x continuous from negative 1 to 1? It is, and I'm going to talk about why in just a second. F of x is continuous on the interval from negative 1 to 1 because if you pick any number between negative 1 and 1 and substitute that in, it fits all 3 pillars of continuity. The other thing is if I temporarily call this y, well, then this becomes y squared equals 1 minus x squared plus y squared equals 1. So the graph that we're looking at is a semicircle, just the top part, right, because we have the positive square root, with a radius of 1. So from negative 1 to 1, we are continuous. To figure out if f is differentiable, we need to find the derivative. So I'm going to think about this as f of x equals 1 minus x squared to the 1/2 power, which means f prime of x equals 1/2 1 minus x squared to the negative 1/2 times negative 2x using the chain rule. So the x's are going to, or the 2's are going to cancel out, sorry. So I get negative x over the square root of 1 minus x squared. is this continuous between -1 and 1? Yes, which means the original function, f of x, is differentiable. Because the only place that we have any discontinuities on differentiable, I can spell, the only place we have any discontinuities on the blue function, the f prime, would be if the bottom was equal to plus or minus 1, but we're not including plus or minus 1 in our intervals, so we're all good. The last thing that I need to check is f of -1 equal to f of 1, and the answer is yes, because f of -1 is going to be 0, and f of 1 is going to be 0. So, by Rolle's theorem, there exists C on the interval from -1 to 1 such that f prime of C equals 0. Okay, but then this one says go a step further, and it says find the C value. So I actually want to know what is that C value that makes my derivative equal to 0. Well, this right here says take f prime of C equal to 0. This was f prime of x. Let's look at f prime of C. So you can choose to substitute in your x values with the C value if that makes it easier for you to see. Pun intended. I said it, I didn't actually do it. So you can put the C's in there, or you can still just solve for x, and that's fine. We're going to set this equal to 0. Solving for C, I'm going to multiply by the square root over to the other side. So I get just when is the numerator equal to 0? Numerator will be equal to 0 when C equals 0. And if we think about a graphical representation, here's our secant line, and at C equals 0, we have our tangent line that has a parallel slope, a slope of 0. Last one. Can Rolle's theorem be applied on any interval? If yes, state one such interval, find the values. If no, state no such interval exists, explain why not. Well, the first thing we want to check is f of x continuous? So f of x to the 2/3 would be that we square the number and take a cubed root. And f of x is continuous from -infinity to infinity. Now, what ends up being tricky is that in order to find the f differentiable, we have to take f prime. So f prime of x will be equal to 2/3 x minus 2 to the -1/3 power, which means I'm really looking at 2/3 cubed root of x minus 2. And hopefully you guys will be okay to say that f prime has a problem spot at x equals 2. So f of x is differentiable. Because remember, to be differentiable, it means the derivative is continuous on all real numbers except for 2. Which means that if we're going to pick one of these, pick an interval, right, for this to exist, for Rolle's theorem to apply, rather, we need to think about what does this graph actually look like? Can we find an f of a equal to f of b so we could create an interval, a to b, knowing that we have to skip over 2? Well, let's think about what this graph looks like. This is a bird graph. F of x minus 2 to the 2/3. This one's shifted to the right 2. Notice we have this point of non-differentiability, which is why we're differentiable everywhere except 2, right? Our derivative confirms that. So if I try to set up my f of a equal to f of b, this whole side is decreasing, right? This whole side, f prime, is less than 0. This whole side, f prime, is greater than 0. Is there ever a place where f prime is equal to 0? No, there's not. And it's because if you were to try to pick endpoints, anything that you would set up so that you had a secant line that was 0, right, for a slope, you'd have to push over this non-differentiable point. So if I chose 2 points over here for my secant line, there's not going to be a place because my function is increasing that entire time. These 2 dots will never have the same heights to make that f of a equal to f of b. So in this case, no, because there is no interval a to b such that f of a equals f of b without including the cusp. And so if we include the cusp, then our function is no longer differentiable. So we cannot say that this function would fit Rolle's theorem.